Right, so good day everyone. So today we are going to present about the CFD analysis of compressible flow in a convergent nozzle. So without further ado, let's check it out.
Assalamualaikum. We are from Group 23. We'll be presented about our project, which is the CFD analysis in compressible flow of the convergent nozzle. So this project focuses on compressible flow through a convergent nozzle. Compressible flow occurs when the fluid changes significantly. Typically, a mesh number is greater than 0.3. So as the air passes through the convergent nozzle, pressure energy is converted into kinetic energy, causing the velocity to increase while the pressure and temperature decrease. In this study, ANSYS Fluent and CFD was used to simulate the analysis and analyze the pressure, velocity and density distribution to better understand the compressible flow characteristic of the nozzle. For our objective, first one is to connect the accelerating compressible flow inside and downstream of a converging nozzle with ideas from fluid kinematics. Second, using the formulation found in the reference paper, simulate compressible flow via the converging nozzle using the differential versions of conservation loss of mass, momentum, and energy. And the last one is to apply the CFD simulation to the converging nozzle in ANSYS Fluent.
Here I'll be presenting the theoretical framework for our converging nozzle analysis. We are studying gas flow where density variation becomes significant as pressure gradient change. Unlike incompressible flow, we must couple thermodynamic properties with kinematic flow motion whenever the Mach number exceeds 0.3. The Mach number, our primary governing parameter, relates local velocity to speed of sound, which is itself determined by the gas temperature and specific heat ratio. To analyze acceleration, we utilize isentropic flow relations which idealize the process as adiabatic and reversible. This equation provides a framework to calculate how static temperature, pressure, and density drop as the fluid accelerates. A fundamental characteristic here is choking, which impose a physical limit on mass flow. As back pressure decrease, velocity increase until the flow reach sonic condition or Mach equal to 1 at the throat. At this critical point, the mass flow rate reached its theoretical maximum, serving as the benchmark for our nozzle's performance. However, these analytical models assume ideal conditions and cannot easily account for losses like turbulence, frictions, or boundary layer development. To address this, we transition to numerical model using CFD tools like ANSYS Fluent. By solving the full Navier-Stokes equation, we simulate the actual physical behavior of the gas, providing a much higher resolution view of pressure and velocity distribution than hand calculation allow.
Next is the literature review. The first is Khan et al. 2021 used ANSYS Fluent to simulate compressible flow through a nozzle. Second, the study examined the effects of different nozzle pressure ratios on flow behavior. Third, results showed pressure, temperature, and density decrease, while velocity increased along the nozzle. And lastly, CFD accurately predicted nozzle performance, making it a reliable alternative to experimental testing.
Moving to the nozzle design, our system utilizes a converging diverging profile with a 20-degree convergent angle and a 5-degree divergent angle. The inlet diameter is specified at 25.9 mm, while the throat diameter is at 7.7 mm to provide the necessary contraction ratio for our target Mach number. For the downstream geometry, the divergent section measures 13.2 mm in length, followed by an extended duct of 60 mm. This specific configuration is typically for research environment as it allows us to effectively study shockwave behavior and the overall efficiency of the isolator. In this study, the cross-section area changes smoothly throughout the geometry to prevent flow disturbance. This design choice is critical for maintaining stable supersonic flow conditions, serving as the physical domain to validate our numerical results against theoretical mass flow prediction.
So move to the methodology of simulation. So there is two. After we are designing the nozzle, we are going to see. We are going to the step of meshing and simulation. So firstly, I'm going to talk about the mesh generation, which is the meshing. The method we are going to use the quadrilateral dominant, which is we want the square to be dominant, and then the element size is 0.5, which is the larger than the journal, which is the journal is default, and because we are going to cut time for the simulation. And then the solver reference, which is the fluent, because we are going to use the CFD, which is the fluent in the ANSYS. Alright, so after we complete the meshing, we are going to do the CFD setup. So this is the setting, which is the setup of the fluent we are going to use. So the model, the energy on, which is we want to do it in the compressible flow, and then the viscous is standard KE because we want to also see the effect of loss of energy from the viscosity, and then density, and then all the material, the boundary condition, and we are going to run the simulation. Right, so after we run the simulation, this is the iteration or the result overall. So we can see there is this is the graph of the fluctuating and the velocity and the KE graph. So as a result, this is the pressure result, which is we can see in the contour. The convergent one, the higher, and then entering the throat, and then it's dropped in the supersonic boundary, which is we are going to talk after this. So the maximum pressure at the pressure at the throat is 3.37 times 10 to the power of 4, which is lower than the we said earlier, because there is a pressure drop of the on the throat. Okay, we're moving on to the result of the velocity. As we can see, this is the opposite of the pressure because the relation of the pressure and the velocity are going to be opposite. So as we can see, the throat have the magnitude velocity of 293 meter per second, and then this is the result of the density of the nozzle. So as you can see, it is similar to the pressure because it is similar to the pressure, and then the density at the throat is 1.65 kilogram meter cube. So as you can see here, it is similar to the pressure. So as you can see, there is a pattern diamond. So we are going to talk about this next, and then there's a fluctuating on the after throat. Okay, we moving on to the explanation of the result. So as we can see, there is a two output from the result actually. First one is at the throat, and then the second one is at the after the stroke, which is the sonic regime. After this lah, I'm going to talk about. So firstly, we are going to talk about the sonic regime transition, which is the throat. The air velocity at the throat actually reached 2.93 meter per second, confirming that the flow successfully achieved sonic condition, which is similar, which is in about Mach 1.0. Actually, if we key in the number to the formula, we are going to get the velocity of sound is higher than 2.93, but why it lower than the sound velocity? Because there is a energy loss due to viscosity and friction, and then this indicate but somehow it is successfully achieved the sonic because it is similar to, it's in about the Mach 1.0, and it indicate the choke condition on the throat. So the static pressure dropped sharply to 3.37 times 10 to the power of 4 due to conversion of pressure kinetic to energy to the within the convergent section. And then the local density, which is at the throat, reached 1.65 kilogram meter per cube as a direct response to the expanding gas behavior. Now we are going to talk about the supersonic acceleration, which is the after the throat. Downstream of the throat, the divergent geometry allowed the compressible gas to expand further, accelerating it into the supersonic regime, which is more than 1 Mach. So shock diamond train formation, as we can see at the contour of the result. The pressure, velocity, and density profile display distinct fluctuating wave-like pattern, which is like the diamond one inside the extended duct. So this physical phenomenon validate the presence of the oblique shock wave and expansion fan. Okay, so at the end of the extended duct, we can see the pressure adaptation actually. So this wave structure form because the flow must dynamically adjust the internal pressure to match the ambient atmospheric pressure, which is as we said earlier in the boundary condition, which is the Pascal gauge at the outlet.
So in conclusion, the CFD simulation successfully analyzed compressible flow through the convergent nozzle using ANSYS Fluent. The result shows that pressure decreased while velocity increased toward the nozzle throat, which agrees with the principle of compressible flow. Density also varied throughout the nozzle due to changes in pressure and temperature. Overall, the simulation was consistent with theoretical prediction, demonstrating that CFD is an effective tool and reliable tool for analyzing nozzle flow behavior. That's all from us. Thank you.